At the largest scales, the universe speaks a language of elegant simplicity. It's the language of general relativity, Einstein's masterpiece. It tells us that space bends. It's a smooth, continuous fabric, a dynamic stage on which the cosmic drama unfolds. Massive objects like stars and planets create deep wells in this fabric, and the curvature of space-time tells other objects how to move. This is gravity, not a force pulling from a distance, but the very geometry of the cosmos. We see its effects everywhere, from the gentle arc of a thrown ball to the majestic dance of galaxies across billions of light years. It's a theory of profound beauty and predictive power, tested and confirmed for over a century. But zoom in, way in, down to the realm of the unimaginably small, and the universe speaks a completely different language. This is the world of quantum mechanics. Here, smoothness gives way to granularity. Certainty dissolves into probability. Particles jitter. They don't have a single position or a single path, but exist as a cloud of possibilities, a superposition of every potential state at once. This quantum world is governed by uncertainty and frantic, ceaseless fluctuations. It's a world of discrete packets of energy, of quantum leaps, and of an interconnectedness that defies our everyday intuition. And just like relativity, it is one of the most successful theories ever conceived, forming the bedrock of our understanding of matter and energy. For most of cosmic history, these two languages, these two fundamental descriptions of reality, have been spoken in different domains. Relativity for the very large, quantum mechanics for the very small. They work perfectly in their own realms. But there are places in the universe where these two domains are forced to collide, and right where they meet, at the edge of a black hole, where immense mass is crushed into an infinitesimal point, or in the first instant of the universe, when all of existence was smaller than a single atom, our best ideas flat out disagree. The two pillars of modern physics crumble. The problem isn't just philosophical, it's mathematical. Here's the hook. When I take the beautiful geometric equations of gravity and try to apply the established rules of quantum theory, the rules that work for every other force of nature, the math blows up. It spits out infinities, not elegant, meaningful infinities, but nonsensical ones. They appear in calculations of probabilities, telling us that the chance of something happening is infinite %. This is a signal that the theory has broken down. It's like asking your calculator to divide the universe by 0. The conflict is simple to state, but brutal to solve. To find a theory of quantum gravity is the single greatest challenge in physics today. So what's the solution? There are several contenders, each a radical reimagining of the universe. The most famous is string theory. It proposes that the fundamental constituents of reality aren't point-like particles, but tiny, one-dimensional, vibrating strings. On this view, everything we see, an electron, a photon, a quark, is just a different note, a different vibrational mode of the same underlying string. The universe becomes a cosmic symphony. By replacing zero-dimensional points with one-dimensional strings, the theory elegantly sidesteps the mathematical problems. The interactions are no longer concentrated at a single point, but are smeared out. Make things extended, and the nasty infinities soften. And the bonus? One particular vibration of the string has exactly the properties of the graviton, the hypothetical quantum particle of gravity. In string theory, gravity isn't an add-on. It pops out naturally from the mathematics. A different approach, loop quantum gravity, takes a more direct route. Instead of quantizing particles on a background stage, it quantizes space-time itself. It proposes that space is not continuous. Area and volume come in discrete, indivisible chunks. Imagine space made of tiny, interconnected loops, weaving a spin network. This network, the geometry of space. There is no in-between the loops. This fundamental graininess of reality puts a hard limit on how small things can get. This means there can be no infinite compression, no singularity at the heart of a black hole or the beginning of time. Instead, you reach a point of maximum density, and the universe bounces. The singularity is an illusion, a sign we were using the wrong tool, a smooth description for a fundamentally discrete reality. Other theories build space-time from the ground up. Causal dynamical triangulations is a fascinating approach that models space-time as being built from tiny, identical triangular building blocks called simplexes. By following a simple set of quantum rules for how these blocks can be glued together, a large-scale, smooth, four-dimensional universe like our own can emerge dynamically, much like the simple rules governing water molecules give rise to the complex behavior of waves and currents. For decades, these ideas were confined to chalkboards and supercomputers. There seemed to be no conceivable way to test them. The energy required to probe the Planck scale, where quantum gravity effects should dominate, is a trillion times greater than our most powerful particle colliders can achieve. But that is beginning to change. A new experimental renaissance is underway, seeking not to create these energies, but to spot their subtle, lingering effects on the world we can access. Physicists are designing tabletop experiments of exquisite precision. In labs around the world, they levitate tiny silica nanoparticles in cryogenic vacuums, using lasers as optical tweezers. They cool them to near absolute zero to quell all thermal noise, creating a pristine quantum system. The goal is to put this tiny speck of matter into a spatial superposition, to have it exist in two places at once. If we can achieve this with two such particles, we can then ask, do they gravitationally attract each other? If the gravitational field between them becomes entangled, it would be the first direct evidence that gravity itself is a quantum phenomenon. It would be a watershed moment in the history of science, proving that the fabric of space-time is not just a classical background, but an active participant in the quantum world. The search is also moving into orbit. Missions are being designed, like the hypothetical quantum gravity gradiometer Pathfinder, to take this precision to a global scale. Such a satellite would use atom interferometry, a technique that leverages the wave-like nature of matter. Inside the satellite, clouds of ultra-cold rubidium atoms would be tossed up in a fountain, split into a superposition of two paths by lasers, and then recombined. The subtle influence of Earth's gravitational field would alter the quantum phase of the atoms along each path. The resulting interference pattern would be a measure of the gravitational gradient with unprecedented accuracy. While its primary mission would be to map Earth's gravity for climate science and resource management, such an instrument would be so sensitive it could potentially detect subtle deviations from classical gravity, or even the faint, high-frequency hum of the primordial gravitational wave background, a key prediction of many quantum gravity models. The quest for quantum gravity even forces us to reconsider the nature of time itself. In Einstein's Relativity, time is woven together with space into a four-dimensional block universe. The past, present, and future all exist on an equal footing. The flow of time is seen as a human illusion, but quantum mechanics suggests a different story. The act of measurement, the collapse of the wave function, seems to introduce a fundamental asymmetry, a genuine arrow of time. Some physicists speculate that time is not fundamental, but emerges from a deeper, timeless quantum reality. Experiments at the attosecond scale, a billionth of a second, are now probing the very process of quantum jumps, measuring how long they take. If these transition times vary in ways that depend on gravitational potential, it could be a clue that time itself is a quantum phenomenon, its pace dictated by the geometry of space-time, and the implications may extend even further into the most complex system we know, the human brain. Zooming into a neuron, we find a cytoskeletal lattice of proteins called microtubules. Some bold proposals, like the orchestrated objective reduction or ORC-OR hypothesis, suggest that quantum computations could be occurring within these structures. This hypothesis posits that the collapse of these quantum states is not random, but is an objective physical process, triggered when a superposition becomes massive enough that its own self-gravity makes the state unstable. In this view, each moment of conscious awareness is a gravitationally induced quantum collapse. It's a speculative but profound idea, suggesting that the solution to quantum gravity might not only explain black holes, but also the very nature of consciousness. It's a stunning parallel, the intricate network of neurons in the brain mirroring the vast cosmic web of galaxies. A bridge from the micro to the macro, perhaps hinted at by a deeper underlying theory. So, which path is the right one? String theory, loop quantum gravity, or something else entirely we haven't yet imagined? We don't know. We need more clues from the cosmos, faint echoes and gravitational waves from merging black holes, subtle patterns in the afterglow of the Big Bang, or a definitive signal from a tabletop experiment. For now, as physicists, we keep two maps in our pocket, the quantum map of the small and the gravity map of the large, knowing the real treasure, the ultimate theory of everything, is the one that finally overlays them both. The universe is telling us a deeper story, written in a language we are only just beginning to decipher. We're finally close enough to hear the whisper, and the effort to understand it will redefine our place in the cosmos.